In today's video, we are going to learn about what would be the net electric field due to an infinite thin, non-conducting, positively charged sheet. So we have a sheet here and we have placed the sheet on the XY plane. And suppose we are given the uniform charged density, the uniform charge density equals sigma. So that essentially means the net charge, if it is Q, this Q over A, which is per unit area, we call it charge density, and the notation used is sigma. So we have placed this sheet, infinitely thin, non-conducting sheet, on XY plane. So look here, here's the X and here we have taken this Y and we have placed in this way so that the Z axis is coming out of it. The Z axis is protruding out like this. So if we complete our axis references, we'll have Z minus Z going downwards, then we'll have minus X is going in this way and minus Y would be going in this way. This is how we have placed. So suppose if I take an example, suppose we place this in this way. This is the XY plane. So we have taken this axis as X here, and we have taken Y axis like this, and Z axis is coming out like this, okay? So it is just protruding out in this way, the positive Z axis, and the negative Z axis is going downwards. This is how we have placed this non-conducting sheet, and then we will try to figure it out how we move forward to get the result, which is the net electric field because of this. So we have taken infinite large non-conducting sheet, ideally infinite, however in practical we cannot take an infinite sheet, but somehow we have taken infinite to get an impression that the electric field which is applied, or the electric field, and it's all positive, right? So what kind of symmetry we do have? We have a planar symmetry here. So the symmetry is, it's a planar symmetry example. Planar symmetry. Why? Because this non-conducting sheet is positively charged. So plane, if we consider, the uniform electric field is going upward in the direction of Z axis. So we have got this E vector, the electric field is magnitude of E multiplied by the unit vector K. This is denoting that it's going towards positive Z axis. Similarly, if you take the bottom part of it, it is going downwards, electric field. Similarly, electric field in the direction of negative K cap. And what kind of symmetry? It's a planar symmetry. So keeping in mind this kind of charge distribution, we have taken a Gaussian surface. If we come to this figure is just, we have introduced this Gaussian surface, taking into account that it's a planar symmetry. We have a Gaussian surface, and this is referred to as pillbox. It is the Gaussian surface which is referred to as pillbox. Now this pillbox is tunneling in this way. It is protruding in this manner. It is upwards, and downwards I have shown here, it is tunneling out. So we have taken this for our convenience, this Gaussian surface, and using Gauss law we are going to analyze the situation. We are going to find what is the net electric field because of this situation. So if you want to find what is the net flux, so the net electric flux is going to be integral E dot dA. So this integral is over the entire closed surface. So this closed surface we have. So if you want to find what is this closed surface is made up of, so it has three regions. One is the curved one and the other two are flat surfaces. So this equals one curved surface. So I have taken, for our convenience, we have taken this flat S1 surface, suppose the bottom one is S3 and the curve we have denoted as S2. So if you take the curved surface, suppose, so we can write here E is constant, E dot, so it's a dot product, right? So E dot, and we have here denoted A2. So for the curved, it's going to be dA2 plus, and we also know from our understanding that these two flat surfaces are equal. I mean, A1 is equal to A3, right? We have denoted this surface, the bottom one, as A3. So this is elemental area A3. There we have elemental area A1. So basically we do have A1 is equal to A3, which is equal to A, suppose, or whatever. Or let's be this, A1 is equal to A3. So just to let you know that these quantities are actually equal. The E value is going to be equal. The flat surfaces are exactly equal in terms of its quantity, quantity wise. So we can add this 2 and we can take this E, any one, suppose we take dA1. Why? Because it's equal, twice of it, and we'll write it here, this is flat. So over curved, this is what it is, and over flat, this is the integral of E dot dA1. So we find here, for this flat one, the angle between the electric field E and the angle area vector dA3, or you take the angle between E and angle between elemental area dA1, it's going to be what? Just try to figure it out. If it is bottom part and it is in this direction, right? So what it's going to be? Can you think that? What angle it's going to be? Figure it out. So this is curved and these two are adding it up. So here we'll be getting the values because the angle is 0 degrees. However, if you look carefully in case of curved surface, the angle here is 90 degrees. The angle between electric field and elemental area dA2 is 90 degrees. Here we will be having the values. Okay, so if it is 90, if you are going to operate over curved surface, it's going to be integral curved. So we get E dA2 cos 90 degrees, and here we'll have plus twice of whatever you take. For one, it holds for second one as well. So it's going to be E dA, magnitude of this, magnitude of E vector, cos 0. So we are going to have the value E dot dA. Well, now here cos 90 is 0, everything goes 0. So this, for the curved one, it's going to be 0. So the net electric flux over the entire closed Gaussian surface, E dot dA, comes out to be just the contribution of these two flat surfaces that we have. Well, so we can remove this for the curved and we'll write that the net flux is this. So this is going to be the net flux, net electric flux. All right. So if you operate this, it comes out to be integral E dot dA. E is what? E is a constant. We'll keep out of it. So let us just remove this and rewrite it again. So we'll write it again. So this comes out to be net flux, which is E dot dA is equal to twice of E integral. Now it's going to be dA1 over flat. Well, E1 is equal to E2 and dA1. So how much it's going to be? This is going to be, if you evaluate what is the area of this, right? Surface area, the complete area. So for this, twice of this, it comes out to be the total area. The area of this is equal to the area of that. So it comes out to be, since it's equal, it comes out to be 2EA. Total area, if you take area of the flat surface as A. So we have taken area as a flat surface. Well, so twice of EA comes out to be the total flux. This is total flux. And by Gauss law, this total flux is equal to the charge enclosed divided by epsilon naught. So we will write here, you can take down the steps in sequence, and we have just as of now evaluated what is the total flux, and we have come up with this equation that the total flux is going to be twice of EA. This is what we get. So I'm rubbing this, and then we'll apply the Gauss law here to find what is electric field. So by Gauss law, we get net electric flux should be equal to the charge enclosed divided by permittivity of free space, which is epsilon naught, and we have already found what is net electric flux, which is twice of EA, and charge enclosed. So we have this sigma given, right? So sigma is total charge divided by per unit area. So if you take the area as A, right? So therefore the enclosed charge is going to be sigma times A divided by epsilon naught. A gets cancelled out. So we get therefore twice of E, or electric field E, magnitude of electric field comes out to be sigma divided by twice of epsilon in the denominator. So this is what we get. This is what we get as electric field. Sigma divided by twice of epsilon naught in the denominator. This is what we get, the electric field. Now this electric field, be mindful of the situation that it is symmetrically, right, above and below. So we have here two situations. We can write it here. So if you have electric field wherein this one we are taking the z-axis. The z, if you are taking in the positive direction, which is more than 0. If you are taking more than 0, then electric field is going to be sigma divided by twice of epsilon naught. If you take a situation which is negative z-axis, that is z is less than 0, then we'll take this value E should be equal to negative of sigma twice of electric epsilon naught. Why? Because if you mention the vector sign here, it would be k cap, here it would be minus k cap in the situation when we have the z-axis in the direction of negative z-axis, which is less than 0. So extremely important conclusion that we have drawn from this. Based on this, now we'll have few situations. How do we apply this? Suppose we take two non-conducting sheet and we have different surface charge densities. What is now then would be, those are suppose both positive, or both, or one of the positive, one will take equal to the other, or we can take two similar but opposite nature, one plus, one minus. Then we'll figure out in that situation what would be the net electric field in between those two non-conducting sheets if are placed in close proximity. Until now we have just deduced that the electric field because of a positively charged non-conducting sheet is going to be this. For positive z-axis it's going to be sigma divided by 2 epsilon naught. For the negative z-axis direction it's going to be minus sigma dot divided by 2 epsilon naught. So take it down and then we'll move on to application of this particular result to a situation. So let me rub this area and now come up with a situation that we have two plates, same sheet, having known that what should be the electric field, we will apply this, applying the result, applying this result in the situation given. Suppose we do have one sheet like this, the another sheet is here. Well, and this is sigma 1, suppose this is sigma 2. And we want to find these two are positively charged, suppose, and we want to find what is the electric field outside here and what is the electric field here. So if you take this direction, it's going to be out, both are positive, it's going to be out, here it's going to be out. So let us take this sheet as sheet number 1, let this be numbered as 1. So this we are numbering as 1, this we are numbering as 2. Okay, so because of this having surface charge density sigma 1, we'll have electric field going out in this way. And because of this, we'll have electric field going in this way or in this direction. And similarly here, it's going to be uniform in this way, in this direction. Well, so here, because of this, right? Because of this, it's going to be what? Suppose this sigma 1, suppose we take sigma 1 to be more than sigma 2. All right, if it is more than sigma 2, the area, the surface charge density is different. And what's going to be the electric field? So here it's going to be net electric field. So because of this E1, we can write this E1 is equal to what? So E1 is going to be sigma 1 divided by twice of epsilon naught in this direction. Okay, and E2, similarly it is, because of this, E2 is going to be sigma 2 divided by twice of epsilon naught. Similarly here, it's going to be this E1. E1 is going in this direction, so we can write E1 here is going to be sigma 1 over twice of epsilon naught. And because of this itself, it's going to be E2, and this comes out to be sigma 2 divided by twice of epsilon naught. But here it's going to be, since sigma 1 is more than sigma 2, so we can write here the net electric field is E1 minus E2. Okay, so here what's going to be the net? It's going to be E net here. E net here is going to be in this region, suppose this is region 1, this is region 2nd, this is 3rd region. So in the first region, we'll have net electric field adding up of this, because it's in the same direction, it will be sigma 1 plus sigma 2 divided by twice of epsilon naught. So this is going to be E net in region 1. Here in region 2, it's going to be E1 minus E2. So E1 we know it is sigma 1 over twice of epsilon naught minus sigma 2 twice of epsilon naught. So this comes out to be, if you subtract this, we can write in this way, sigma 1 minus sigma 2 divided by twice of epsilon naught. This is electric field, net electric field in region 2. So this region. Well, in this region again, it's going to be E net. In region 3, it's going to be this sigma 1 plus sigma 2 divided by twice of epsilon naught. So this is going to be in region 3. This is one application that we can have here, having known the result. We can take other situations as well and apply the result to figure out what would be the net in different regions. So suppose now we take both same, So this is the first case. If you take here both same in the sense the surface charge density is same. Suppose if it is same and both are positive, then we'll just use this result and we'll use sigma here. So it becomes sigma 1 is equal to sigma 2 is equal to sigma. So it is twice of sigma divided by epsilon, twice of epsilon naught. So here in this region it would be E net would be in this region, in region 1. In this situation it would be sigma by epsilon naught. So what's going to be in the middle? In the middle, this E net would be 0. Why? Because sigma 1 minus sigma 2, it's cancelling out, so it becomes 0 here in region 2. Here similarly, here in the third region you would have E net as sigma over epsilon naught. Why? Because this is adding up. Okay, now this is the second case. This is the second application that we have discussed. Okay, what would happen if you have a situation? So let us demarcate this with this line. Now we have another. So this was case 2, this was case 1, and now we are discussing case 3. In case 3, suppose if I take sigma here and if I take opposite negative sigma here. And now we are interested to find in all the 3 regions what would be the net electric field in all the 3 regions. So in this one, we'll put sigma 1 equals sigma 2 in terms of magnitude, but the nature is different. So it comes out to be here sigma 1 minus sigma. Why? Because it's going to be minus, so here it's going to be E net equals 0. In the middle part of it, sigma is equal. However, this negative and negative would become positive, and here it would be twice of sigma divided by twice of epsilon naught in the denominator. So we will have net here in this region as sigma divided by epsilon naught. Similarly, in the third region, which is outside here, it's going to be the same, which is adding up. So we'll have here E net as 0. So this is a situation that we'll use later on when we'll be using capacitor. So you'll keep in mind, and then we'll derive that equation. So but not now we know that here the E net value is going to be sigma by epsilon naught. And what's going to be the direction? The direction is going to be from positive to negative. The electric field runs from positive to negative here in the middle part of it. So these 3 applications actually clears all the concepts. All the concepts related to this result, how we are using in those 3 situations. So firstly, we tried to figure out what would be the electric field. Then we have applied this to 3 situations. Take note of this, and then we'll move on to the next concept in electrostatics, which will be of electrostatic potential energy, electrostatic potential. So watch the next video. Thank you.